so that I can put it on YouTube later and you can see it again if you want to. Okay, so we are going to start with the periodic table. I'm going to share my screen and I'm going to show you something that we started last time when we were looking at the periodic table. And I'm going to just remind you of a few little bits and pieces to do with it. Firstly, you had to know that the vertical columns are called groups and the horizontal columns, horizontal rows are called periods. That's easy. You have to know that group 1 is on the left and it goes through 1, 2, 3, 4, 5, 6, 7, and then 8 or 0, the noble gases. The 3 groups that you need to know most about are the alkali metals, group 1, a little bit about group 2, then group 7, and the noble gases. Not that there's very much chemistry to do with the noble gases. So what we're going to do today is we are going to look at the periodic change, in other words, going across a period. That is quite important. So that is where we are going here. And they normally ask questions about the period sodium to argon. They expect you to know about that. So that is what we're going to be looking at first. Sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, argon. Please mute whoever that is. Okay. So the sort of things you need to know about are these. Firstly, you need to be able to work out the electronic arrangement for each of the elements. That's not very difficult. Not very difficult at all. I'm sorry, I'm getting a sound from my phone. Just a moment. Okay. So what we've got is the elements going across the top: metal, metal, metal. Metalloid, that means it has some properties of a metal and some of a non-metal. Then we've got non-metal, 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 and non-metal, although it doesn't really react properly. The bonding and structure you need to know. Please mute. Please mute. Hi guys, we really have to mute. Thank you. Thank you very much. The bonding and structure going across, well, the first 3 are all metals. So the bonding is metallic. You probably know about metallic bonding, but I will look at it very briefly. Then we have a giant covalent. Silicon is exactly the same structure as diamond, but with silicon atoms in there. Then phosphorus, sulfur, chlorine, and argon, and we will come across how they are set up. Now, the trends you need to know about. Firstly, you need to know about the sizes of atoms as you go across the periodic table. Now, if you're going to write this down, can I suggest that you do this? Guys, can we mute? Thank you. Is you do something like this. If you draw a little periodic table, and it has to be nothing more complicated than this there, and let's say I'm doing atomic size, which is normally called radius, then I can say, okay, this way it gets smaller, and this way it gets bigger. So that's all the notes that I really need. Okay, that's what I would do for each one of these trends. That's the easiest way to make a note. Okay, I'll just get rid of that. Oh, why does it not do that? Okay, so here we go. So firstly, atomic size obviously increases as we go down a group. If we look at lithium, it only has 2 shells. It is 2,1. Sodium is 2,8,1, 3 shells, potassium 2,8,8,1, and so on. So each element, as we go down a group, has a new shell, a new energy level, so they get bigger. That is easy. But what about going across a period? It seems a little bit surprising. If I look back at this, lithium has 3 protons, 3 electrons, beryllium 4, 5, 6, 7, 8, 9, 10. You might think, oh, they're going to get bigger, but they don't, they get smaller. Here is the atomic radius across period 3. And it shows a big drop at the beginning, less change later. The reason for this is that across any period, all of the electrons go into the same shell. Okay, so let me just write on this. So across a period, all the electrons go into the same shell or energy level. Means the same thing. But, and this is the big thing, the number of protons increases. Because the number of protons increase from sodium to magnesium, magnesium has a more effective nuclear charge. The nucleus is better at pulling the electrons in. So if I look at sodium, it has 11 protons, 12, 13, 14, 15, and so on. Now that means that by the time we get to argon, argon has nearly twice as many protons as sodium. Well, that means that it has twice as many protons pulling the outermost electrons inwards. So, third period, let us say that this is the sort of the distance out that the energy level is. So the third shell or third energy level. Here's sodium, it has 11 protons. Magnesium, the electrons are in the same sort of distance from the nucleus, except that instead of 11 protons, it has 12, and therefore it is a little bit closer. So 11 protons, 12, 13, 14, 15, 16, 17, and so on. Across any period, it is the same. More protons, electrons going to the same sort of radius, distance, and therefore the protons are more effective pulling them in. Okay. So that's a really important piece of information. The next thing we need to look at is ionization energy. Ionization energy is the amount of energy that any element, when it is a gas, turns into a positive ion as a gas, losing 1 electron. Please mute. Please mute. Thank you. This is the first ionization energy. Now, as far as KCSE is concerned, these 2 drops here and here do not count. So you can think of it as simply increasing. Okay? Can you mute, please? Can you mute, please? Thank you. So first ionization energy increases left to right across period. Okay, The first ionization energy increases across a period. That is the most important thing to start with. St. Michael's, I'm muting you. Please stay muted. Thank you. So this is the first key piece of idea, that the first ionization energy increases left to right. That looks like left to B, left to right across the period, increases. Why does it increase? For the same reason as this. If the atoms are getting smaller and there are more protons, then the protons will hold the electrons better as you go across. And therefore, the ionization energy increases. It's a very simple, very important idea. Let's just change this to an R. Whoops. So left to right, ionization energy increases. For those of you who are interested, these two drops here for aluminium and sulfur are due to what we call subshells. And some of you may have come across the idea that the third, which we're dealing with, the third shell consists of subshells. This is the third energy shell, okay, energy level or shell. And it consists of s orbitals and p orbitals, and they make up the third shell. There are 2 in the s and 6 in the p, and then there are some 3d as well. They're not important as far as you are concerned, but for those of you who want to be chemists, this will be important eventually. Okay, so ionization energy increases left to right because the atoms are getting smaller and the nucleus is becoming more effective. The next one is about the melting point. The melting point looks like this across the group, across the period. So sodium is much higher than these guys over here, but it goes sodium up to magnesium. There's a very slight up to aluminium, then it's up to silicon, down to phosphorus, sulfur, chlorine, argon, which are all much lower. But phosphorus is a bit lower than sulfur, and phosphorus is a bit higher than chlorine, and chlorine is higher than argon. Now, the reason for this is that the first 3 are metallic bonding. We already said that. Okay, they are metallic bonding. Let me just get back my... Okay. So you're going to be answering lots of questions in a minute, so I hope you're listening. So these first 3 here are all metallic. Now, metallic is ions, positive ions, close together, held together by delocalized electrons. I'm sure you know this. Delocalized electrons are floating in between them, so they are around all of them, between them, and so on. The strength of metallic bonding depends on the charge on the ion, the number of delocalized electrons, so these are delocalized electrons, and these are cations, these are the positive ions, and it depends on the charge, the number of electrons, and the size of the ions. So because sodium forms 1+, and magnesium forms 2+, and aluminium forms 3+, the aluminium will have 3 times as many electrons in the delocalized, Magnesium, twice as many as sodium. Silicon is giant metallic. But sorry, what am I talking about? What rubbish? It's not giant metallic. My apologies. Come on. Thank you. I'm going bananas. Giant covalent. A best example of this is diamond, okay, which you know. Now, these guys down at the bottom, phosphorus goes around in 4s, sulfur goes around in 8s, chlorine goes around in 2s, and argon goes around as monatomic single atom molecules. All of these have van der Waals forces. And van der Waals forces are proportional to the number of electrons, which is a little bit like size per molecule. Now that means that this has got 18. This has got 2 times 17. This has got 8 times 16. And this has got 4 times 15. Don't worry about those numbers, but it just shows you why there's this little change here that sulfur is the highest because it's the most atoms joined together. So P4S8Cl2Ar. Now they normally only ask you about these two, about why chlorine and argon have different boiling temperatures or melting temperatures. Okay, let's go on. The next one is about electrical conductivity. The metals all conduct, obviously, and they're good conductors. They're not the best conductors. The best conductors are things like gold, but they're not bad. And they are good conductors because they have delocalized electrons. Silicon is a poor conductor, but it is a conductor. If it wasn't, you wouldn't be able to hear me because my computer wouldn't work and it uses silicon in its semiconductors. All of the next 4 are simple molecular, in other words, individual molecules, covalent, and they are non-conductors or insulators. Okay, that's important. Simple electrical conductivity goes like this. Actually, this is what it looks like in more detail. Sodium is not a bad conductor. Magnesium is better. Aluminium is the best. It's the same as metallic bonding. This is 1 delocalized electron for each atom, 2 for each atom, 3 for each atom. Silicon, a little bit higher than all of these guys. These guys, basically just insulators, just non-conductors. This one's semiconductor, but nothing like as good as these, the metals. So these, fewest electrons, most electrons, best conductor. You have to know about thermal conductivity. That is the conduction of heat. It is really simple. Basically, metals conduct heat and non-metals don't. Now, there are some like carbon and silicon and arsenic and antimony which do conduct, and carbon actually in diamond is one of the best conductors of heat there is. But in general, just think metals are really good conductors, which is why we make them into saucepans and so on, frying pans, and non-metals do not conduct well. And it's because the conduction of heat is done by metallic bonding, holding the atoms and transferring heat vibrations through it. Okay. Any questions so far? because you're going to do some questions now. Are you okay? Are we okay? I hope we're okay. We're going to be okay. All right, let's have a look at some questions. Let's see if we can do some nasty KCSE. Thank you for that thumbs up. Some nasty KCSE questions. I've lost my questions. Oh, here we are. Okay. Excuse me. Let me just make my board a little bit different. Right, I hope you can see that question fine. I'm going to ask each one of you to have a go at this each. Just have a go at it. I'll make it a little bit bigger there. Have a little bit of a go at each question, and then we will go through it. So because these are 1 mark each, and there are 3 of these, draw the electron, dot, and cross diagrams to show the bonding in nitrogen and fluorine, and then say why fluorine is more reactive. I'd like you to try writing it down, but if you don't write it down, have a think about it and then talk to your neighbor, somebody next to you at the desk, and see if you agree about the answer. Okay? I will be sending these questions and the answers to your teachers in case you're not sure about them later. So I'm going to give you a few minutes now just to have a look at them while I get a glass of water. And I want you to try and think, can I draw nitrogen, which goes around as N2, and fluorine, which goes around as F2, and then say why fluorine is more reactive than nitrogen. Just see if you can do that while I get a glass of water. If you're not sure or you don't feel confident about this, do not worry. I will go through it with you. Okay, each bit I will go through with you. If you need a copy of the periodic table, I will show you it. Here's the periodic table just for a moment. Nitrogen is here at the top of group 5 and fluorine at the top of group 7. Okay, so nitrogen is atomic number 7 and fluorine is atomic number 9. Okay. There's the periodic table. Here's the question. Two minutes more. I hope everybody is having a go at this. I will be very interested if somebody wants to show me their answer. I will be very... Oh, we have somebody from Dandora Girls trying to show me. Hang on, let me just get a bit closer. Excellent. That's very good on the bonding. Now, can you answer the next question? That's very good. Dandora, who... Oh, hey, hang on. Atomic radius. That's absolutely correct if it was an atom, but it says with reference. It says with reference to the diagram. With reference to the diagram. Does anybody else want to show me their picture? Their pictures. Come on, Sir Michaels, you can do it. Come on, Mathari Mixed. I know you can. Come on, Silver Spring. Dandora has shown us the way. Glory? Come on. Come on, Glory. Have some courage, some braveness. St. Mary's. Right. Let's look at the question. Okay. Now, nitrogen is 2, 5. So therefore, each atom needs to gain 3 electrons. Fluorine is 2, 7. So it needs to gain 1 electron each. Okay. Now, we know that it's N2 and F2, so we start by drawing overlapped circles because they're covalent, so they will share like this. So this is N, N, F, F. Now, this nitrogen here on the left needs to borrow 3 electrons from the other one. So I'm going to put 3 in here. I'm going to put 3 crosses in here. At the same time, the one on the right needs to borrow 3 from the one on the left. So let's put 3 dots in. Some people put it very neatly. It doesn't matter. We have to remember that nitrogen had 5 electrons to start with. And therefore, 3 are in here. And therefore, there must be 1, 2 outside, 1, 2 outside. This would be shown as nitrogen triple bond nitrogen. Fluorine only needs to gain 1. So this one has to borrow 1. This one needs to borrow 1. Fluorine had 7, only 1 in there. So 1, 2, 3, 4, 5, 6, and 1, 2, 3, 4, 5, 6. So this would be fluorine single bond to fluorine. Now, somebody from Dandora gave me a really good answer about why fluorine is more reactive than nitrogen. But they didn't answer it with reference to the diagrams. What they said was, fluorine only needs to gain 1 electron, and it's smaller, and therefore it is better at gaining electrons than nitrogen, which is true. But that isn't the answer they want here. What they want here is, it is easier to separate the F atoms than the N atoms. That's because N triple bond N is more difficult to break than F. So it's in with reference to the diagrams. In other words, it's talking about this, and that's very important. Okay. Any questions? I'll come back to it, but any questions now? Does anybody have any questions now? Are we okay? Are we okay? Mathari's okay. Wamwini's okay. St. Mary's. St. Mary's are okay. St. Mary's have loads of thumbs. Kabiro's okay. Silver, you guys are great. Some people in Silver Spring not sure. Hey, well, what the heck? So let's go back to the questions. Okay, here's the next question. This is about group 2. Now, part of this question is quite difficult. It's about phenolphthalein, but just look at the question first. It says we've got 3 tubes, some beryllium in one, magnesium in one, calcium in one. Here's the periodic table again. Whoops, where's it gone? Where's my periodic table gone? Ah. Can't periodic table share. There's the periodic table. So here they are. Beryllium, magnesium, calcium going down. So if you remember from group 1, and it's the same in group 2, they become more reactive as you go down. So here we have 3 test tubes, beryllium, magnesium, calcium. They're put in cold water with phenolphthalein indicator. Now, you may not have come across phenolphthalein yet, but phenolphthalein is colorless unless it is in alkali. If it is an alkali, it goes pink. Okay, that's an important thing that you have to know about phenolphthalein. It's a funny word, isn't it? But phenolphthalein is pink in alkali and is colorless otherwise. State and explain the observations that were made in each of the following tubes, 1, 2, and 3. Have a moment. See if you can work out what might happen and why, because it says 2 points here. It's very important that you state and explain. State is tell me what you're going to see, and explain why. So let's have a few moments where you have a go at this. See how you get on. Oh no, there are some people in St. Mary's on the second desk on the right-hand side who are trying to get some sleep. So everybody be nice and quiet. Uh-oh. Come on, Kabiro. Let's get some work done. Go on, let's have some thinking, some writing down. Beryllium, magnesium, calcium. What would you expect to see? 3 tubes, all with water. What do you think? So in the periodic table, Those are their proton numbers, atomic numbers. So this will be 22, 282, 2882. Show me again, Dandora. That's very good. There are some other observations, though. It's not just about the phenolphthalein going pink. I'm going to just remind everybody about something, and that is that group 2 do something very similar to group 1. When they are in water, group 1 elements do this. They form the hydroxide and hydrogen. It balances like this. Now, the NaOH, doesn't balance like that. It balances like that. The NaOH splits up to form Na plus and OH minus, and this is the alkali. Whoops, what is happening here? Come on. Sorry about the mess. So the OH minus is the alkali. And the same sort of thing happens with group 2. Dandora have shown me an answer. I'm going to go through it now. Anybody else want to show me an answer? Dandora showed me a very good answer. Anybody else? Okay, I'll show you my answers. I'm going to start with test tube 3 because it's more important in some ways to start there. I just need to be able to get rid of some of this. So I've got some room. Hang on. Okay. So I'm going to start with calcium. So what actually happens, it doesn't ask you to do this, but what actually happens is this. Calcium reacts with with water to form calcium hydroxide and hydrogen. If I have 2 waters, then that makes sense. This is alkaline, okay? So that overall, I will see this reaction, I will see this given off, and so I see bubbles first. You might want to say effervesces or something like that, but if you just say bubbles, that's good. You can say the calcium disappears because it does. It's all gonna go. That's gonna disappear. And actually, this is white, solid, because calcium hydroxide is not very soluble. Appears, and the phenolphthalein goes pink. Now, the other two are going to be much slower. Oh, sorry, I've just written all of that under test tube 2 rather than test tube 3. My apologies. This is for calcium. It should be test tube 3. The point is that because calcium is the biggest atom, it will react fastest. So the magnesium will be slower and the beryllium will be slowest still. So beryllium probably almost nothing happens. And it does. Pink slowly appears, but there's really no bubbling and so on. It's really, really slow. Magnesium would be a bit quicker and calcium is most. So in state, they're all going to go pink, but this is going to be slowest, then faster for magnesium and fastest for calcium. Because of bubbling, the first one will hardly bubble at all, the second one very slow, and the third one much quicker. And the answer to explain is because as we go down the group, they become more reactive. Any questions? So beryllium really slow, magnesium really still quite slow, calcium quite quick. Calcium, because it's the biggest atom, so it loses the 2 electrons most easily. Right, let's go to another question. Here's this is a question from paper 2. The longer questions are always from paper 2. Paper 1 is much simpler. So here's the sodium to argon period. Very simple to start with. Give the formula and name of the compound formed between Al and S. And then explain the variations in the atomic radius across the period, and then the one with the highest ionization energy, and give a reason. Everybody have a go at that, please, first. Kabira, you want to show me something? Oh, wait, that was very quick. Well done, Kabira. That's very fast. Well done. Somebody at Kabiro just showed me the formula already, and Mathari, I think, is going to show me the same thing. They are very good. Well done, guys. That's very, very good. St. Mary's. Oh, hold it. Come back, St. Mary's. Let me have a look. Up a bit, I think. Yes. Well done. Good. Excellent. Well done. Now, what's its name? What's its name? Aluminium. I'll give you a hint. It's got aluminium in it. So its name will be aluminium something. Aluminium what? St. Mary's, a little bit closer, please. It's not Dandora. It's not aluminium silicate. Very good, St. Mary's. St. Mary's, get the gold medal. Aluminium sulfide. That's really, really good. Well done, St. Mary's. Come on, somebody else. St. Mary's have got it right. Silver Spring, you're out of focus. A little bit further away, I think. Possibly it will be in focus. It doesn't focus. If you hold it completely in front of the camera because it is trying to focus on you. Kabiro, atomic radius decreases, period left, right, increasing number of protons. Very good. Yes, well done, Kabiro. We're getting good here. Silver Spring, let me have a look. Yes. Yes, Silver Spring, good, excellent. Many, many good students today. Well done. Come on, Sir Michaels. Have some courage to show me your answers. Come on, Glory. You're looking very smart, Glory, but we need some answers. Most people have got the first one. This is going to be Al2S3, and its name will be aluminium. And then it's S, not Si. Always check. Oh, yes, S. So that's sulfur. Doesn't matter whether it's F or pH, really doesn't. And because it's only 2 elements, it's I'd, not 8. If you get 8, it's got oxygen in it. Now, the atomic radius, if you look at it carefully as it goes across, basically gets smaller. So it doesn't say I need to say that, but I'm just helping myself remember. Now, there are 2 marks. If there are 2 marks, they are probably looking for 2 points. So why does the atomic radius get smaller? We just did it. That's very good, Mathari Mixed. Dandura. Doesn't have the largest. Oh, Na, because, okay, yeah. Think about ionization energy, Dandura. Very good, Kabiro. Just think about ionization energy is about
this is due to the
losing
this
electrons.
is due to the increase in the number of protons, which led to the increase in the force of attraction.
That is absolutely right, St. Mary's. That's absolutely right. Well done. I hope everybody heard that. It was a very good explanation. So let's have a look at the question. So the atomic radius gets smaller because, and I'm going to put it in this way, increasing number of protons. I could say makes the nucleus or the nuclear charge more effective, pulls the outermost electrons in more, so the atoms are smaller the further across we go. Which element has the highest ionization energy? The one, if you remember, I said that ionization energy was about it losing an electron, the highest ionization energy. In other words, it is X, whatever X is, having to lose an electron to form a positive ion, an electron. And it is that energy, okay? That energy. We have to put energy in to do it. So the one which is most difficult to lose, well, that means it'll be on the right-hand side. It'll be on the right-hand side, and it'll be the one which is, in this case, argon. It has the smallest atoms and most, sorry about my handwriting, effective nuclear charge. So electrons are difficult to remove, or something like that. Okay. Now, this question goes on. So here we are. It says first, write the electron arrangement of phosphorus in PCl3, and then select an element which forms an ion with the smallest radius. Okay, an ion with the smallest ionic radius, and give a reason. So write the electron arrangement of phosphorus in PCl3. Phosphorus, I'll just go back up just for a minute. Here's phosphorus. Its atomic number is 15 to start with. Well, it always is. So write the electron arrangement of phosphorus in PCl3, and then select an element which forms an ion with the smallest radius. So have a go at those two questions there, please. Just think, wow, that's very fast, St. Michael's. And Dandora Girls' School, well done. That was very fast. Well done. Now do the more difficult one, which is the second part. So phosphorus, when it is bonded in PCl3, just think if you were drawing a dot and cross diagram, how many electrons would phosphorus have now? Exactly the right answer, Dandora. Gold medal. Kabiro. Phosphorus, Kabiro. Phosphorus would have started at 285, but what does it gain from the 3 chlorines? If you draw a dot and cross diagram, how many electrons are now in the outermost shell, or the outermost energy level of the phosphorus? Sorry, Silver Spring, show me again. Yes, that's right, Kabiro. Silver Spring, if you change your video camera at the bottom and you say, and you uncheck blur my background. Okay, so if you go down to video, video at the bottom left-hand screen, and you uncheck blur my background, I will be able to see your work more. Anybody else like to have a go at this? We've only got about another 10 minutes or so. Let's see if we can get some more done. Can you manage that, Silver Spring? Okay. I'm going to just do this. So I'm going to, this is not what it asks me to do, but I'm going to just draw phosphorus trichloride. P, Cl, Cl, Cl. Phosphorus started as 285, chlorine as 287. So each chlorine needs to gain 1, and the phosphorus needs to gain 3. So we end up with this. And then phosphorus is in group 5s, so there are 2 more here. Now that means in phosphorus's outer shell now, there are 1, 2, 3, 4, 5, 6, 7, 8. In other words, it becomes 2, 8, 8. So there, 2, 8, 8. The element which forms an ion with the smallest ionic radius, well, the ions will be Na plus, Mg2 plus, Al3 plus. Carbon doesn't really form one. Oops, sorry, silicon. then phosphorus will be 3 minus, 2 minus, 1 minus. Now it can't be any of these because they are bigger than the atom. This is the size of the atom. And these three here, this will be the smallest. So Al3 plus is the answer. And the reason is it has lost its outer electrons and has the strongest, almost effective, nucleus out of those which have lost electrons. Okay, so sodium, that has 11 protons, magnesium has 12 protons, aluminium has 13 protons. So once it's lost its outermost electrons, the aluminium will pull in most. Next question. Have a go. We mentioned this and we mentioned this right at the beginning of the lesson. See if you can remember. So sodium and magnesium, look at those. Magnesium is much higher. Why is it much higher? And chlorine and argon, chlorine is quite a bit higher. They're both gases, but chlorine is higher. Okay, Dandora. Well, thank you very much for being here. And I'm sorry you have to go, but thank you very much for being here. And I'll say asante sana and kwaheri. Bye now. So who's going to get the gold medal? Come on. Who's going to get the gold medal on this one? So we want to know why magnesium has a much higher melting point than sodium, and why chlorine has a higher one than argon. Anybody remember? We've only got just over 5 minutes. These are questions which keep on coming up in KCSE. They keep on coming up. They are very common questions. Right, come on then, let's have an answer from somebody. Come on, Mathari. Come on, St. Mary's. Come on, Kabiro, Glory, Wamuini, St. Michael's, Silver Spring. Let's have somebody with an answer. Why is magnesium so much harder to melt than sodium? And why does chlorine have a higher melting point than argon, even though they're both gases? If we cooled them down to under the sort of temperatures we have here, argon would melt and boil much quicker than chlorine. Why? Come on, we've only got 5 minutes. Quickly, save the world. Oh, Mathari, we have an answer. Correct. Mathari Mix gets it right. Sodium on the chlorine argon. It's not. Very well. Second bit, very good. Kabiro, second bit, really good. About magnesium, but the sodium bit, it's not van der Waals. The magnesium, it has very strong metallic bonds, but why? They both have very strong metallic bonds. They both have very strong metallic bonds. Why? Sodium and magnesium, they're both metallic. So why is magnesium higher? Okay, I'm going to do it. Are we ready? Okay. Na and Mg, both metallic. That's very important. Okay. But Mg forms Mg2 plus, Na forms Na1 plus. So Mg has twice as many delocalized electrons and its ions are more attractive. So metallic bond is stronger. Now, chlorine goes around in diatomic molecules and argon is monatomic. So they both have what you call van der Waals forces. These are proportional to the number of electrons. Cl2 has more electrons. If you work it out, if chlorine is number 17, so it's 2 times 17, which is 34 per molecule, than Ar, which is going to have 18, because it's a single atom. So stronger or more, doesn't matter which way you want to say it, van der Waals forces. That's the answer. Okay, so sodium and magnesium both metallic. Magnesium loses more electrons. Chlorine and argon both non-metals, simple molecular, only van der Waals between them. But van der Waals depend on the number of electrons, and chlorine, because it goes around in pairs, has more. Okay, now I'm going to send you this question here, which is a very good question. I'll send it to your teachers, and it has, I will send it with the answers, but I'd really like you to have a go at this because it's such a good question. Okay, but now, asante sana, and it's time to run out into the sunshine and stop work and finish. Okay, so I'm going to stop the recording.